First of all, we want to thank to the organizers for their kind invitation, especially Professor Karapetian. But also I want to congratulate to professor from the Institute of Mathematics of the Armenian Academy of Science, because they are celebrating their 80th anniversary. Okay, so the lecture today is about hypercyclic properties and lambda commutants. And let me to say something about the structure of the talk. So first of all, we will try to motivate the problems. Okay. Later we will introduce some basic definitions. You continue formulating questions, and we will try to expose the result, avoiding technicalities when it is possible. Okay, because we don't have time for proof of some technique. We will point out some tools, but just a little. Okay. So why to study hypercyclic properties and lambda commutant? Why these two names? Both concepts are connected with the invariant subspace problem. For instance, answer in the negative sense to the invariant subspace problem are connected with construct or to find operators with large manifolds of hypercyclic or cyclic vectors. On the other hand, lambda commutants are concerned with also with the invariant subspace problem, but in the positive sense. Okay, because commutant, lambda commutant, bicommutant, and so on determine the structure of the operators. Okay. What we want to speak here is that hypercyclic properties usually are transferred to the commutant. And the question today is, general question is to know how this hypercyclic property are transferred to a bigger set, which is the lambda commutant. So, okay, this is the idea. Some basics. So, what is a hypercyclic operator? A hypercyclic operator is a suppose that you have a continuous operator defined on a Frechet space. So we say that the operator is hypercyclic if the orbit of one element is dense in the space. In such a case, the vector is called hypercyclic for T, and T is hypercyclic. If the orbit is not dense, but multiplying by the scalar, that is, the projective orbit is dense, in such a case, the operator is called supercyclic. Okay? And if the orbit is not dense, and multiplying by a scalar is not dense, but with the help of the linear span, the orbit is dense, the linear
for all lambda, or just particular lambda? Given lambda, you take orbits, or
no, for all lambda. We consider the projective orbit. Okay. And if with the help of the linear span is dense, then the operator is cyclist. Supercyclicity stands in the midway between hypercyclicity and cyclicity. And hypercyclicity is connected with the invariant subset problem, because the closure of the orbit of one element is the smallest subset, closest subset contained in X. And the closure of the linear span of the orbit is the smallest closed subspace contained in the vector X. So this notion is connected with the invariant subset problem, and this one with the invariant subspace problem. Okay? And motivating also was this problem it appears in the literature what is a hypercyclic subspace. We say that a hypercyclic operator has a hypercyclic subspace if there exists an infinite dimensional closed subspace H such that any vector here for except 0 is hypercyclic for T. And we say that the operator has a supercyclic subspace if the operator has an infinite dimensional closed subspace of supercyclic vector for except 0, okay? This notion are also motivated by the invariant subspace problem or subset problem, okay? Okay. And lambda commutativity. Lambda commutativity means commutativity up to a factor. So commutativity where the factor is complex. But this terminology was introduced by John Conway and Gabriel Pragitura. It's not correct because, well, it's correct. I like it. But so these properties, this relation is not symmetric. This is not symmetric. And now the people are using the following notation. We say that an operator is T. Lambda is an standard eigenvalue for T if there exists a non-zero operator with its called standard lambda eigenoperator of T such that this equation is satisfied. But the order is important. The order is important. Tx equal to lambda xt. So commute up to a factor. Okay, lambda. This is, and the lambda commutant of an operator is the set of all non-zero operators that satisfy this equation for some lambda. Okay. Why lambda commutant? So, sorry. Lambda commutant appeared in a result was independently proved by the Scott, Brown, and Kim, Moore, and Pierce. They proved that Lomonosov, the famous Lomonosov theorem on the invariant subspace problem, is true not only for commutant, but also for lambda commutant. If one operator has a non-trivial compact operator in his lambda commutant, the operator has a non-trivial hyperinvariant subspace. You know, so simple terminology. So let us see some examples of hypercyclic vectors and hypercyclic operators. Probably this is the first, seems to be the first examples of hypercyclic operators. We denote H of C, the space of interior function with a compact open topology. And Birkhoff proved in 1929 that the translation operator is hypercyclic on H of C. And some years later, MacLean proved that the differentiation operator also is hypercyclic on H of C. Okay? These seem to be the first examples of hypercyclic operators. So, general question is the following. I say, cyclic and hypercyclic property are transferred to the commutant in some way, and we want to know how happened for the lambda commutant. Here, there is an example. In 1991, Just Godefroy and Joël Shapiro characterized, unified the classical result by MacLean and Birkhoff in the following sense. L is an operator which is in the commutant of the differentiation operator. Automatically, if it is not a multiple of the identity, it's hypercyclic. In particular, D is hypercyclic, and the translation commute also with the differentiation operator are hypercyclic both. Okay. This theory is quite surprising because there is not analogous in the Banach space setting because contraction are not hypercyclic. His proof is based on an exotic description of the commutant of the differentiation operator. The commutant of the differentiation operator can be expressed by phi of d when phi is an entire function of exponential type. Okay? And the specific question 1 is the following. How hypercyclic properties are transferred to the lambda commutant of the differentiation operator on H of C? Okay? Second example of hypercyclic operator. This is the first example of hypercyclic operator on Banach space. We denote by B the backward shift operator, which is just the operator that shift on the right the coordinate. B acting on the basis A0 is equal, this is the canonical basis on LP, and B acting on En is n minus 1 for n bigger than 1. This is the backward shift operator, okay? And Rowley proves that lambda B is hypercyclic if and only if lambda is a complex number. The modulus of lambda is bigger, strictly bigger than 1, okay? Again, we have a characterization of, we can see in the same paper of Godefroy and Shapiro how hypercyclicity of the backward shift are transferred to the commutant. The commutant of the backward shift operator is just the adjoint of any analytic Toeplitz operator. Okay? An analytic Toeplitz operator, they prove that it is hypercyclic if and only if the image of phi of d, which is a point spectrum, intersect the unit circle. Okay, this is they characterize. And the specific question 2 is how hypercyclic properties are transferred to the lambda commutant of the backward shift operators. Okay, defined on the hard spaces 2. The first step in order to get some result is to give a complete description of the lambda commutant of a given operator. The lambda commutant of a given operator is a very difficult, complicated subset. But in this case, when the operator is D, the lambda commutant can be, the element in the lambda commutant factorized in a specific way. The operator R, the form R lambda, where R lambda is the dilation operator, and phi of D is an element in the commutant of the differentiation operator. So with this factorization theorem in the hand, we can attack the problem before splitting the proof is splitting in several cases depending on the values of lambda and the properties of phi. Okay, this is a consequence of this factorization theorem. And let me introduce a distinguished element in the lambda commutant, but we back again to Godefroy and Shapiro result. Okay, just a moment. Godefroy and Shapiro result say that, please keep in mind the role of the identity. Every element in the commutant which is not a multiple of the identity. So the result pivot around the identity. Okay, keep in mind. In no result, the statement will pivot around another operator, a distinguished operator. We say that this map, we will say that this map is an affine endomorphism. Sorry. We say that this map is an affine endomorphism of the plane, and we consider this composition operator. Okay, a composition operator induced by affine endomorphisms. Okay, this is a special case of lambda commutant, and this operator was proved by Bernal and Montes that is not hypercyclic never for a set when it's a translation. Okay, and moreover, later it was proved that it is not supercyclic for a set when it is a translation, lambda equal to 1. Okay, this operator is never supercyclic and hypercyclic. Okay, and here we have the first result, the main result. Here you have a standard lambda Degen operator of the differentiation operator. Then the operator is hypercyclic if and only if the modulus of lambda is bigger or equal to 1, and L is not a multiply of a composition operator induced by an affine endomorphism of C. You can see the analogy, replacing identity by affine endomorphism, composition operator induced by affine endomorphism. But much more is true. Recently, we was able to prove not only this characterization, we proved that this operator is frequently hypercyclic. Frequently hypercyclic, I explain later, if and only if the same condition is satisfied. This result is stronger because this phenomenon is stronger. One operator is said to be frequently hypercyclic. Okay, of course, if it is hypercyclic, but much more. For any open subset, if we consider that the number of times that the orbit visits this open subset, okay, this set, okay, is a big set in the natural number, has lower positive density. So the orbit visit the open set many times, okay, very often, frequently. This is the idea. And here we see, we denote by H of C the set of hypercyclic operator, by SC the set of supercyclic operators. This is our second main result about supercyclic element in the lambda commutant. We was able to prove that we have a standard lambda eigenoperator of the differentiation operator. Then the operator is supercyclic and not hypercyclic if and only if the modulus of lambda is less strictly than 1. L is not a multiply of a composition operator induced by an affine endomorphism, but much more. It appeared this condition for us was an unexpected condition. Phi of 0 must be 0. Why is an unexpected condition? Because Vladimir Müller proven a long-standing question in the theory that every non-scalar operator, not multiple of the identity, that commute with a generalized backward shift is supercyclic. Okay? Of course, D or operator D, the differentiation operator, is a generalized backward shift. Its behavior is very, very near to the backward shift. Okay, it's a weighted backward shift, in fact. Okay? And what has a corollary, we say that Vladimir Müller result is not longer true for the lambda commutant of an operator. Okay, not every operator that lambda commute with a generalized backward shift is supercyclic. We continue. Okay, we break a little. This is one of the tools that we use. This is the hypercyclicity criterion, universality criterion, which means that if you have a sequence of operators and you have a big control of the power of the sequence of operator on dense subset and on the sequence of the right inverse. This mapping are the right inverse. Okay. Then you have a big control on dense subset. You have chaotic behavior. You have an element which orbit is dense. This is what means the hypercyclicity criterion or universality criterion. Okay. One of the main tools that we use in our paper. But let me to say something about some selected background. Okay. The history begins with sorry. What?
Why do you need the subsequence?
Yes, there is some sequence. It is sufficient to obtain control on a subsequence.
So can you? So TMF is dense, but then you want everything to hold on the subsequence. So if you drop the assumption of the subsequence, then this is no longer true. If you just require that just TA goes to 0, is it immediately equivalent to this formulation?
No. Well, if not exactly. No, there are different kind. No. For the full sequence, it is another notion than hypercyclicity. Okay. So the history begins a little before Godefroy and Shapiro, in the work of Bossamy. Bossamy constructed an operator on Hilbert space. We have a manifold, dense linear manifold M, okay, whose non-zero elements are hypercyclic. So Bossamy constructed a pre-Hilbertian counterexample to the invariant subset problem. But later, some years later, Godefroy and Shapiro on the space of interior functions say that constructed or founded more natural examples of with the property of Bossamy, having a dense manifold, invariant manifold, whose non-zero elements are hypercyclic. Every element in the commutant of the differentiation operator has this property. Moreover, Paul Bourdon proved that any hypercyclic operator on Banach space or on Fréchet space has this property, okay, has this manifold. However, not all hypercyclic operator has an infinite dimensional closed subspace of hypercyclic vectors. So there is some operator which are more hypercyclic than other one, okay? In a strong contrast with Bourdon results. In this sense, we found in the literature these three results: Peterson, Scarin, and Menert. It is so-called Peterson, Scarin, and Menert result. These three mathematicians prove that any element that commutes with the differentiation operator has a hypercyclic subspace. Okay? Well, this is the selected background. And here is our result. Let us denote by H of C the set of hypercyclic operator having a hypercyclic subspace. Okay? And suppose that we have L an standard lambda eigenoperator of the differentiation operator. And the table below summarizes is a full characterization of when an standard lambda eigenoperator has a hypercyclic subspace. Okay, this part is consequence. It must be shadow, but it's not shadow. It's consequence of the previous result. 5 minutes. Okay. So just a little. How to find a hypercyclic subspace? The same criterion, hypercyclicity criterion, plus an extra hypothesis. You have also control on an infinite dimensional closed subspace in the space. Not only we have a hypercyclic vector, we have an infinite dimensional closed subspace of hypercyclic vectors. We can say for supercyclic subspace. For supercyclic subspace, the table below, pues, summarize is a full characterization of a standard Lagrange operator that have a supercyclic subspace. Okay, the result depends of the zeros of the function phi. It's not the same that the function phi has a finite number of zeros, that the function phi has infinitely many zeros. Okay, each element in the table work with different proofs. Okay, and new ideas. And let me to say something about our recent advances about the backward shift operator. So for the backward shift operator, first we have a description of the commutant which is a little different from the description of the backward of the differentiation operator. If modulo of lambda is equal to 1, then we have this factorization when phi is an element, is a bounded analytic function. But surprisingly enough, when modulus of lambda is less strictly than 1, we have this factorization when phi is an element in H2. It's curiously this factorization because the lambda commutant, we discovered that an example. The lambda commutant is an special. We consider the operator algebra, the lambda commutant that we obtained. So it's a special case of operator space. An operator space is just a closet, and it's a subspace of H. And there is a lot of literature about operator space, okay? But moreover, this operator space is Hilbertian. It's a Hilbertian, a natural example of Hilbertian operator space. And this is the characterization for the hypercyclicity of the lambda commutant of the backward shift operator. 2 minutes. Okay. We have a theorem which is a trichotomy. Okay. And we also characterize when the operator, the standard Lagrange operator, as supercyclic. Again, appear this condition. Okay. It's not strange that appear the same condition because backward shift and the differentiation operator has some similarities. Okay. And finally, this material can be found in these papers. This is the paper. This is the journal that we will publish, Alexei, which is the chief editor, Alexei, and this is still on revision, but we can find the paper in archive. Okay, thank you very much for your attention.